So chapter 11 are the hypothesis tests for means. And I mean, this is going to be pretty much the same as it always has been. It's not that much different than a hypothesis test for proportions. It's not even that much different than the confidence interval for means. So it's not going to be a huge stretch, I don't think. We're going to start out doing this the easy way. I figured that might be the best way to do it. I'm going to try it out. We're going to do this the easy way first, all right? The way you would actually do it on a free response question using the calculator and everything. So that way you can see the whole, the whole picture. And then once you get that idea pretty well done, then we're going to actually look at it the hard way. What is the math that's actually happening here? Even though our calculator is doing most of the heavy lifting for us, right? So we'll see how far we get along with that. If we get through all that, then your video lesson will be on some two-tailed tests a little bit. If not, I will sort of finish this lesson off with the video. I haven't made that because I'm not 100% sure how far we're going to get. So giving myself a little bit of a cushion / leeway. All right, you ready for this? Let me get my piece of paper here, my digital piece of paper. You got a piece of paper to write some things down on so you stay awake? All right, you better hit submit. So let's do this. Are Amazon basic batteries better than name brand Duracell batteries? So Duracell has been making batteries for decades using the Bolt battery runtime test. It's a thing, look it up. Their batteries will last an average of 30 hours. So our question, is there convincing evidence at the alpha equals 0.05 level that Amazon basic batteries last longer? So we take a SRS of Amazon basic batteries and perform the Bolt battery runtime test. Here is the sample data. All right, so we got our sample data there. Time to do our hypothesis test on that. Do we have convincing evidence that this lasts longer than the Duracells? So, state, we will test so our null hypothesis is that they're the same. Okay, is that they're the same, that the mean is equal to 30, that the Amazons are exactly the same as the Duracell. No news, nothing special. Our alternative is that they're better, right? So the mean will be greater than 30. Mu will be greater than 30. Now, I used a variable mu. I have to define that. Where mu is the true average runtime of Amazon basic batteries using the Bolt battery runtime test. All right, so that's what we got to do for state. Our null, our alternative, and then we have to define our variables. All right, moving on to the plan part of this. So we have to state what procedure we are doing. We are doing a one sample t-test. Now, all right, not an interval, like what was on your quiz in the Desmos last time, right? It's not an interval. It's not a confidence interval. It's a test. A one sample t-test for mu. All right, which is a population mean. A one sample t-test for a population mean. All right. Next, all of our conditions. Do we meet the conditions? So the random condition. Did we meet the random condition? This one is met because we have an SRS of, what was it, 15? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, of 15 Amazon basic batteries. All right, quick thing that I see sometimes in people's work, okay? You want to actually say somehow that the condition is met. All right, sometimes as simple as a check mark would do, I think, even. But you have to somehow say that the condition is met. Otherwise, you're just stating things, okay? It's like my kids at the dinner table. This drives me nuts so much. We're sitting at the dinner table, and like my son Michael will just say, water. Yeah, water's a thing, bud. I know. It's kind of important too. I like it. What about it? All right. You can't just say SRS of 15. Yeah. What about it? Okay. Why are you saying SRS of 15? What's it to you? So make sure that you somehow say that the condition is met. Otherwise, it's just like, yeah, good job. Water exists, bud. My water's quite tasty. How's yours? So I have to make him ask. All right, the 10% condition. All right, so this is met. It is safe to assume that our sample of 15 batteries is less than 10% of... All right, again, what is our population? The population is what you are sampling from. We are sampling from Amazon batteries, right? Not Duracell. So 10% of all Amazon basic batteries. Next, the normal/large sample, also called the large counts, right? I didn't realize this, I think, but I think in the book they use large counts for proportions, and then they started calling it this for means. I don't think the name really matters. I mean, you're doing the same thing. You are making sure the sampling distribution is approximately normal. But they have started labeling it this way, the normal/large sample condition here. Well, shoot. Our sample size is less than 30, right? Oops, I don't need that bolded. Our sample size is less than 30, so we have to look at the sample distribution. All right, we have to graph the sample and see, could our sample have come from a normally distributed population? All right, so I got to graph this somehow. Which your video was on, right? Hopefully you feel pretty good about how to graph this one way or another. I mean, you could just do it by hand. You just want to make a quick dot plot by hand. You could do that if you wanted to, okay? Might even be faster sometimes to do a dot plot by hand. But I'm going to type it in here to mine. Actually, I think I already have it in here, don't I? I do. So you type it into the calculator, 17, 32, 22, 45. You can go ahead and pause the video if you want to type that in before we keep going. But I'm going to keep going. It's an oldie but a goodie, all right? It's an oldie but a goodie. So I typed those numbers in. I want to graph this. So I'm going to go graph. I have to make sure set up for the Casio, set that up, make sure it's on maybe a histogram, I guess, would be great, from list 1. So I can just hit graph. So for my histogram, what are the last two? The last two numbers? Oh, that's right. There you go. My bad. So I'm going to start at 10. So yeah, that start point, what's the lowest number? I think 17 is the lowest, so I'll start with 10. The width, the largest one is 45, it looks. No, 51. So if I have to go from 10 all the way up to 50, I don't know, you can count by 5s, you can count by 10s. Doesn't really matter. I'm going to count by 10s. Look at that. Beautiful, symmetrical. No issues there. Now, if this is a free response question, you do need a picture of that. All right? There we go. I'm not sure why that messed up all of a sudden. So, I'm going to draw a quick sketch of that, all right? Let's see, I started at 10, and then I was counting by 10s. 20, 30, 40, 50, and then I'll probably go up to 60, right? And on the Casio, if you hit Shift Trace, Shift F1, all right, so my first bin from 10 to 20, it is 1 tall. I might even put a 1 over that. And then my next bin, it is 3 tall. So from 20 to 30, it is 3 tall. Oops. Next one is 7 tall. Next one looks like it's also 3, right? And then 1. Wow, nice and symmetrical there for us. Perfect. You do need to include that graph so that it is obvious how you came to this conclusion. This condition is met because our sample distribution does not have heavy skew or outliers. So that is a perfectly reasonable way of doing that. Again, you can do a dot plot by hand if it's faster than typing it into the calculator for you. That is also fine. It doesn't have to be anything amazing looking. You just need to have some kind of a picture to justify why you are saying this. Okay? Why you are saying that. Alrighty, time to do the do. Well, wait a minute. If I'm going to type this in, I need the summary statistics, don't I? I need to know X bar. I need to know the standard deviation of the sample. I know the sample size is 15, so my degrees of freedom will be 14, right? But I need the average and the standard deviation, both of which my calculator can give me, right? So if I go exit, one nice thing about the Casio, I will say, is if you're at the graph, if I go back to the graph, F1 is the one variable statistics right there. So once I have the graph, I can just hit F1, and then it gives me everything. The average is right here, 33.93. And the standard deviation, S of X, is 9.8, I don't know, 9.82? Let's round that up, 9.82. Once I have that, we can plug this into a calculator. We are doing a 1 sample. t-test, right? So I need to find that on my calculator and type it in. Casio, man, I like the Casio. It's real easy, right? We go to test. This is a t-test. And this is a one sample t-test. And then we type everything in. On the 84, let's pull that one up as well. We go statistics, tests, and we need to find the one sample t-test. It might just be the t-test at the top because I see a two sample t-test right there. Is there a one sample t-test anywhere? Doesn't look like it, does it? So it must be that top one. All right, now we got to type everything in. So on the 84, make sure under t-test you're not, and you might be able to just put on data if you typed all the data in. Oh, that would be kind of cool. I bet that works. Let's pretend that I didn't though. I'm going to go stats. So what is our null hypothesis? Our null hypothesis is that this is equal to 30, right? Our sample average was 33.93. Our standard deviation was 9.82, right? Yeah, 9.82. And our sample size, so it wants the sample size, not the degrees of freedom. We actually, it'll do the degrees of freedom for us. It wants the sample size 15. What was our alternative? Is that we were greater than the null, right? We think it's greater than 30. So I want the third one here, greater than the null. You can either draw or calculate, whichever one. If you want the picture of the sampling distribution, it's always nice to have a picture, isn't it? Shades in our p-value, and we get a p-value of 0.0717. Get the same thing on the Casio real quick. Same info though, right? Let's see, we want to know that if we are greater than the null. So make sure you type in greater than the null. Our null is 30. Our average is 33.93. And our standard deviation is 9.82 with a sample size of 15. Hopefully you got all that in there. And if you go down, you can also click draw. It'll draw it. And then if you want the p-value, F2 will give you the same p-value, 0.0717. All right. What was our null? So if I scroll back to the top, our null is right here. Is that it's equal to 30. How did we get that? That came from the problem because we are testing our Amazon Basic batteries better than Duracell. And so Duracells last 30 hours. So our null is that they are the same. No news, nothing different, nothing changes. Our null is that they're the same. Our alternative is that our Amazon ones are better, that it's greater than 30. All right, we got our p-value, time to conclude. What was our, I should write what was our alpha again? It's been so long, I forgot. Our alpha was 0.05, wasn't it? Let me double check, my bad. Sorry for the scrolling. Yeah, there it is. Alpha 0.05 level. I probably should have put that here, shouldn't I? Oops, my bad. All right, conclusion. So do you remember? We fail to reject the null hypothesis. All right, our p-value is, which I might as well put number of 0.0717, is greater than alpha, which is equal to 0.05. All right, we fail to reject the null. Our p-value is greater. We do not have convincing. That's not how you spell convincing, is it? Why isn't it giving me the, there we go, evidence that Amazon basic batteries last longer than 30 hours using the Bolt battery test. All right, I'm hoping that sentence sounds familiar, right? We've written that sentence a bunch for proportions. Oh, wait, the evidence that Amazon batteries last longer on average. There we go. We're doing an average, right? Then 30 hours using the Bolt battery test. All right. I'm hoping that sounds familiar, but ask me a question. Anything not seem right to you? Any questions about that process? All right, hopefully. All right, so we're going to practice this a little bit then. How do we find summary statistics on the TI-84? Good question. All right, so that was in the video, but if you forgot, where's my 84? I don't think I have these numbers plugged in. I don't have these numbers plugged into the 84, but it is important, Tricia. So for the, I actually probably should have said true in there somewhere, shouldn't I? I should have put the word true in there, my bad. Maybe I should revise my sentence. To find the summary stats, you've got your numbers plugged in. You go stat, and then calc. And then one variable statistics. All right, we want just the mean and the standard deviation. Those are one variable statistics. You tell it what list your numbers are in. So ours are in L1. There is no frequency list, so you want that to be blank. And then you hit calculate. And then it tells you them. So your mean x bar is right there, and the standard deviation s of x is the next one. Those are not the same numbers, right? I don't know what numbers I have in my 84, so that's why they're different, probably from the video. But you go stat, calc, one variable statistics. Yeah, should I fix my sentence a little bit? This isn't a great sentence. My bad. I got ahead of myself. We do not have convincing evidence that the true mean runtime of Amazon basic batteries is longer than 30 hours. That's probably better. This right here, I think, is the most important part. The true mean runtime. That's the best interpretation. All right, let me throw the link into chat for the Desmos here for your practice. Try this out. It's just one problem, like we just did. I just separated up into a bunch of slides. So it's just one question per slide, but it's the exact same thing we just did, okay? And of course, if you start working and then you have a question, please put it in the chat. All right, this is not a test. This is not a quiz. This is practice. So if you get stuck, please say something. I will be looking through your answers and trying to give you feedback as you go. But if you get stuck, don't stay stuck.